Hello, Dean, KK4DAS here. Welcome to the next edition of the SolderSmoke Challenge Direct Conversion Receiver. Today we're going to talk all about the Bandpass filter. This is the third of our 4 boards in the receiver. But before we do that, I want to give you a little bit of a progress report on how we're doing with the challenge. The good news is our Discord channel is up and running. We've had several hundred people connect. There's about 20 that I think are actively building the receiver that we know of. A few folks have already completed the receiver. Bill's put a few videos up on the blog, and it's gratifying to see that people are actually getting it done. There's a little bit of not so good. We've had some inconsistent results. Some people are not getting enough drive out of the PTO. The mixer builds have been a little bit challenging in terms of getting the mixers to mix properly with the diodes we chose. A few people are struggling still to source parts. We tried to go with things that are generally available. A few things like the J310 probably were a mistake for us to put in the BOM to begin with, because that's for the through-hole ones, at least that part has been discontinued, and there are other FETs that will work there just as well. So we've got some learnings there. And then, with the good and the bad, there's always the ugly. And guess what? We updated the schematics. See, and you thought we knew what we were doing. But the reason we updated them is we're getting experience from other builders. Bill and I have probably built 4 or 5 of these each over the last couple of years. But, we did this in 2023. We were working with the high school students. We never really got to the point where the high school students were really integrating. Several of them had finished the boards, but we hadn't had a chance to really look at a number of builds yet until now. And so we're learning and we're updating as we go. So a couple of things have changed in the schematic. Nothing has changed in the architecture. We still got 4 boards and they're still doing exactly what they said. We had a couple of frankly typos and drafting errors on the schematic. So the big changes in this current version, or the changes, none of them are actually real big, is I changed the L12 and L15 rather, link coils to the correct inductance. Now, the inductance of the link coil is not all that important. What we're really looking at is the turns ratio between like L14 and L15, and that sets the input and output impedance of the filter at about 50 ohms. So the actual value isn't real important. And in fact, these numbers on here are really used by the SPICE simulation. And so we just want to, if we're going to run a simulation, we want to be close to correct. What else did we change? Big change, we changed the diodes. So in the diode double balanced mixer, we're now recommending the 1N4148. The Schottky diodes that we had in there before will work, and I have demonstrated they'll work, but we seem to get a little better switching action with the 1N4148s, and it's likely that there are other Schottkys that would work better than the ones that we had originally chosen. But as I said before, practically any small diode will actually work in the mixer. The whole point is you want enough local oscillator energy to cause the diodes to switch, and they switch the RF, and they switch and cut up the incoming RF, and that's what produces the mixing products out the other end. So we changed those to 1N4148. On the PTO, we discovered that if you add a bypass capacitor to the J310, this is C21 on the schematic here on the lower left, that bypass capacitor increases the output of the PTO and produces better switching action in the mixer. And then the last changes were just some drafting errors in the audio amplifier, getting the C13 or C17, C12, C8 in as polarized caps and showing which way to put them in the circuit. We also changed R14 the emitter resistor of Q4 from 10 ohms to 100 ohms. We'd actually discovered that when we were working with the students, but it just never got changed on the schematic. And one of the things I want to caution you of, if you build things from magazines or other websites, is that schematics almost always have problems. As you can see, even with a relatively small project like this that we've been over many times throughout the years, we still find things from time to time that are wrong. So developing good skills at reading and understanding the schematics is important, and it can be frustrating for a new builder when there's a mistake. Bill has a very well-documented history with the Herring Aid 5 that he never was able to complete building as a youth because of essentially an error in the schematic, which he's documented on the blog. So if you haven't looked that one up, that one's interesting and worth looking at. All right, enough on that. Let's talk about bandpass filters. Let's recall that our bandpass filter is the input stage of our receiver. It filters the radio frequency, and we tune it for the 40-meter band. And it's the thing that eliminates all of the rest of the RF spectrum so that our receiver can be optimized for operating in the band we want it to operate on. So what does it do? It blocks signals outside the 40-meter band while allowing signals inside the band to pass through the receiver. That's why it's called a band pass filter. That's opposed to a low pass filter, which allows signals below a certain frequency, or a high pass, which allows frequencies above a certain frequency, or a band stop, which is used to notch out certain frequencies so that they don't get through. For our receiver, we want a band pass filter, and we need it because the mixer will take in any signal that comes in off the RF port and mix it with the LO, and producing some and different signals. And that will result, if we don't filter before we hit the mixer, that will result in all kinds of spurious mixing products that we don't want. And some of those will end up being at audio frequencies, and we'll hear things in the receiver that are not inside the 40-meter band. So we need a bandpass filter at the front end. And when you finish your receiver, you can test this by seeing what it sounds like with the bandpass filter in the circuit, and then just bypass it and go right into the mixer, and you'll see very quickly why it's important. So let's talk a little bit about the design of the bandpass filter. Now, I'm not going to go into all the math, and I'm not going to go into all of the design constraints, but just a couple of things to kind of get you oriented. Our filter is what's called a double tuned bandpass filter, and that means we have two parallel tuned circuits. And a parallel tuned circuit is LC circuit is an inductor and a capacitor, and the values for the inductor and the capacitor are chosen to produce a resonant frequency, the frequency at which signals will pass through the bandpass filter, that is right in the middle of our band of interest. So the formula for resonant frequency of a LC circuit is well known, and for hams there, it was probably on your technician exam. But we're just using that formula, and we can see that with the values we've chosen, we're going to put our filter right in the middle of the 40-meter band, 7.15 megahertz. We put a couple of those stages together in parallel, and the reason we use more than one stage is it improves the overall filter performance, the shape, bandwidth, and the skirts of the filter, which are the cutoff frequencies. There's a whole bunch of other design considerations that go into building a filter that I'm not going to get into here. There's lots of available tutorials on actually designing bandpass filters and other filters. There are online calculators. Highly recommend the books that we talk about all the time. So Solid State Design for the Radio Amateur, if you can find a copy, or Experimental Methods in RF Design is another good one. You'll hear terms like Butterworth, Chebyshev, and so on. Those are the names of the guys that invented the math that define the shapes of the filters that we're talking about. But we're not going to pay any attention to that for our purposes here. We're really just talking about a double-tuned bandpass filter with basically 2 tuned stages. And so here's what our schematic looks like. On the schematic, you'll notice that there's an R22 1 ohm resistor. Ignore that. That's for the simulation for LT Spice. L12 and L13 are a transformer that's wound on a T50-6 toroid, same as L14 and L15, another one. And basically we have 2 identical circuits, L12, L13, and C18 are identical to L14, L15, and C19, and those are the 2 resonance circuits, and they're coupled by C20, which is the coupling capacitor. The transformers, we use the T50-6. Those numbers tell you what the diameter of the toroid is, 50 millimeter, and the mix, the mix of metals that go into the making of the toroid. And the mix and the diameter and the number of turns are what is used to establish the inductance. There's a great website called toroids.info that is a great calculator. So let's bring that up here and show you what that looks like. So toroids.info, it's run by the Kits and Parts folks, and you can see on the left it's got a whole bunch of different toroids, and we can pick the T50-6, which is what we're using. And if we come to this little calculator here and we put in the inductance value, 3.02, it's going to tell us what the number of turns we need, 27.5, and about the length of wire we need, so 20.4 inches. So I recommend about 21 inches, and we are recommending starting with 28 turns. Now, the performance of these toroids is not highly precise, and there's a little bit of variability between batches. So the 27 or 28 turns is just an estimate. Often you'll see recommendations to add a couple of turns before you build it, and then back off depending on the performance of your filter or the measurement of the inductance. I actually found in my current build that 26 turns turned out to be just about right rather than 28. So even though we say 28 on the schematic, after testing, 26 turns turned out to be about right. And that's been the experience of a couple of our builders as well. So you may want to start with 26 or 27 turns and see how things are working. So let's go back to our presentation. Resume slideshow. There we are. And so that's the story on the toroids. Now the 5 turns, the L12 and the L15, those are link coupling turns that give us a close match to 50 ohms. Now there's a whole bunch of variability in these components, and the way we're getting from the inductance of the impedance, input and output impedance of the filter to 50 ohms is through the turns ratio, the number of turns, and it's the turns ratio squared is the impedance ratio. So you can't put half turns or quarter turns on a coil, so on a toroid. So you're not going to get an exact match to 50 ohms. We had somebody say, well, mine measures more like 100 ohms or 120 ohms. Well, that would be less than a full turn of the link coupling. If you put 5 turns on L12 and L15, you'll be fine. A couple other notes for the capacitors. We're not using fixed capacitors for C18 and C19 and C20. We're using trimmer capacitors in parallel. So for C18 and C19, I'm using a 150 picofarad fixed cap in parallel with a 5 to 50 picofarad trimmer. And that allows you to tune up the filter. If you put fixed caps in, you're going to be doing what we call cut and try, is you'll put 160 in, you'll say, well, that's too much, let's try 150. Well, let's try 170. Now remember, our calculated values are determine the resonant frequency, but there's all sorts of stray capacitance and inductance on these boards that means that the components we're putting down are not the only thing that is contributing to the capacitance and inductance of the filter. So that's why we put trimmers on there, so that we can get it close. Also, we're never going to get exactly 3.02 microhenries out of the inductors, and the capacitors have 5 or 10% tolerance. So putting trimmers in allows us to tune up the filter. I recommend just getting a bag of these 5 to 50 picofarad trimmers from Jameco. They're ceramic trimmers, they're rock solid, they're easy to tune, they're easy to solder in. I'm not a big fan of the plastic ones, the yellow and brown ones that you see on some of the other sites. I found that while they work, they can be finicky, and they can sometimes they'll break or just stop working, stop tuning after a couple of tunes. Couple other notes. I think I needed more than 10 picofarad of coupling in my particular build here, so having a bigger trimmer in there gives you more flexibility. I think I was probably up around 12 or 13 or maybe even 15. I never took it off to measure after I tuned the filter, but that's kind of where we ended up. So a couple of takeaways: maybe 26 turns on the toroids might be a little closer to what we want, and make sure you use the trimmers in parallel. So that's it for the intro. Let's get on with looking at how to build the bandpass filter. So let's get started building the bandpass filter. First, let's take a quick review of the schematic. The filter consists of a tuned circuit on either end, and you've got a inductor at around 3 microhenries and a capacitor at around 164 picofarad. And you couple in and out with another inductor. So these are toroids that are going to be wound with 2 windings, a winding for the tank circuit and then a winding to link out. And the windings are going to be 28 turns to get you around the 3 microhenry, and then 5 turns to get you around the 0.1. Now the actual inductance of this outer one isn't all that important. The inner one sets the frequency. So 3 microhenry, 164 picofarad in parallel gets you to the middle of the 40 meter band. The 2 circuits are coupled with this 10 picofarad coupling capacitor, and that capacitor is what sets the shape of the bandpass, whether it's flat, whether it's undercoupled or overcoupled. So that's called the coupling capacitor. We're going to use a trimmer there, and for these 2 caps, the 164, we're actually going to put a fixed 130 in parallel with about a 50 picofarad trimmer, and that allows us to trim this up and down. So we have a bunch of ways to trim the filter. So let's look at the parts. We've got our T50-6 toroids, we've got our fixed capacitors and our trimmers, and our trimmer for the middle, and then we've got about 21 inches of magnet wire, 2 sets of 21 inches of magnet wire for the tank circuit, and then about 5 inches of a different colored wire. And for this second wire, for the coupling wire, you could actually use a piece of regular hookup wire. You don't really need magnet wire for that. But I just used a different color so that we could see the difference. So the first thing we're going to do is wind the coils on the trimmer, and I'll show you how that looks. Now, just a reminder, when you're winding toroids, each pass through the center counts as 1 turn. So I start by sticking the magnet wire through, and I leave an inch or an inch and a half out because I'm going to need some room for hooking it up. That's 1 turn. Second pass through is 2 turns. And I try and keep it nice and tight as I go. And then 3 turns. And I'm going to just keep going until I get to 28. So I have 28 windings wound on the toroid. They're more or less evenly spread. Should cover about 2/3 of the actual toroid. Next thing I'm going to do is I'm going to take the enamel off the ends and clean them up, and then I'm going to check the inductance just to show you what that looks like. And the easiest way to get the enamel off is just to burn it off. And you can see it just kind of flames up. But once you burn it off, you want to get all that ash off there and get it nice and clean. So I just use a piece of Scotch-Brite. You can use sandpaper, but basically you just want to clean off that little bit of ash so you got a nice kind of shiny copper. So that looks real nice, shiny and copper. Then I'm going to tin those ends, and then I'm going to check the inductance just to show you what that looks like. Now, if you don't have an inductance meter, don't worry about it. You don't really need one at this point, but I'm just going to show you to kind of demonstrate that once you get the 28 turns on there, you're pretty close to where you need to be. So I've hooked up the LCR meter to the coil, and you can see that I'm just a little high. I'm at 3.5 microhenry. Now, because we have caps that we can tune, we can increase and decrease the caps as well. But I'm going to just take one turn off of this toroid just to kind of show you what happens to the inductance. If you just take one turn off, we'll hook it back up now. And there we are at 3.2. And at that point, I'm happy. I've got enough, I can kind of spread out the turns a little bit. And, you know, it'll be close enough for what we want. I mean, if I really wanted to take one more turn off, let's see what happened if I took one more turn off, take it from the other side this time. And that may get us too low. But in which case you can bunch up the coils. I mean, there's a fair amount of flexibility in this once you kind of have it built. So there we are, 3.1, 3.2. So I'm basically right in the zone, and I wouldn't worry about it any more than that. But as I said, if you don't have an LCR meter, you don't need to worry about it. You know, you can see that in this case I took off 2 turns, and that's fine. But if we, when we tune for kind of maximum smoke later, we can make those adjustments later on. Now that we have the 28 turns, now I've reduced it to 26, but now that we have the turns on the winding, we're gonna on the toroid, we're gonna wind the coupling winding right now, and that's about 6 inches of wire. Now the trick with winding the coupling coil is you want to wind it in the same direction as the primary coil. So you want to do it so this one's coming out of the top, so I'm going to put one turn through there like that and kind of keep it all at one end of the coil. So that's one turn right there, and then I'm going to go through and I'm going to make 5 turns. That's 1, 2, 3, 4, 5. Now the end where we started, this is going to be the earth end or the ground end of both coils. And then the other end of the 5 is going to go to the input and of the filter, and the other end of the 28 or 26 turn is going to go actually into the filter. So this end is the ground end, the ground where we started. And it's really important, wind them in the same direction and keep the 5 turns kind of all bunched up at one end of the coil. So now I'm going to build the other one, and then we'll put it all together. Okay, I have cleaned and tinned all the leads. I actually wrapped the two ground ends together and just soldered them together because that makes it convenient, and it's also hard to forget when you've got them soldered together. You know which one is the ground wire. Now I'm going to get some solder on the pads on the board, and I'll put the first toroid down. So again, you want to heat the board and put the solder right on the pad if you can. You want it to flow nice flow of solder. We'll put, let's say, the ground on this one will go on this side, in the middle, and I like to sometimes just make a little dog leg there so it's easy to solder. Let the solder flow over it. There we go. Now we'll get the signal side down. Done. And the last thing we do is get the input side soldered down. And there we go. Watch the solder flow right over the lead. Done. So the first one is soldered in. Then I like to just kind of physically kind of put it down so it's kind of out of the way. And we're good. So now I'm going to get the other one ready and solder that in, and then we'll do the capacitors. So the coils are on. Now it's time to solder in the trimmer. Now I'm just holding that gently in the hemostat. I don't want to break the ceramic, but I do need something to hold it with. And you'll see I put a nice blob of solder on the ground plane, and I got a lot of solder on the pad, and I've also tinned both of the leads. I just wanted to show you how to kind of put one of these on because these can be a little tricky, and if these aren't on good, then your filter's not going to work right. So I'm going to start with the ground side here. And I'm just going to make sure that the solder flows up and over that pin. Put a little heat on both sides. Now I'll do the lead. I'm trying not to put too much downward pressure. I don't want to bend or break things, but when the solder flows over it, should be good. Yeah, so that's a nice, good connection. All right, so now I'm going to do the other trimmers and the fixed caps, and we'll come back and take a look. So here's the completed bandpass filter. All the parts are soldered in. Those are the fixed caps, the trimmer caps, the coupling trimmer. So next thing I'm going to do is kind of show you a couple of different ways to test this. Now, if you don't have the test equipment, it's okay. This is going to work pretty well as is, and when we get it hooked up to the fully built receiver, we can tune it by ear. But if you have some test equipment, we're going to take a look at that. First, I'm going to show you how we test it using the NanoVNA. Then I'll show you how to test it using an oscilloscope and a signal generator. So to test with the NanoVNA, the first thing you need to do is calibrate the NanoVNA, and I'm not going to go through that here. There's plenty of videos on the internet to show you how to do the calibration. But I've set mine up so that the center frequency is 7.15 megahertz and the span across is 5 megahertz. So it's all calibrated, ready to go. I've made a couple of little adapters here that I'm going to solder onto the board, just tack solder onto the board so that I can hook up the SMA connectors. When you're doing a filter through test like this, it's good not to use alligator clips or anything like that. You need to use good connectors in order to get a reliable measurement. So I'm going to put the adapters on there, hook up the NanoVNA, and we'll take a look at the performance of the filter. So here's the test on the NanoVNA. I'm centered at 7.15 megahertz. I have a span of 10 megahertz. Now the filter shape overall doesn't look too bad, but the coupling is wrong. You can see that dip in the middle. You'd rather have it be nice and flat in the middle. So you need to increase the capacitance because we're undercoupled. Let's see if we can flatten that out. And as I'm adjusting the coupling capacitor, you can see the shape of the filter flattening out. That looks pretty nice. It looks like we're right about center, and we've got a nice flat pass band. We've got about 3 dB of loss. With a filter like this, sometimes I can get it down to 1.5 to 2 dB. Sometimes it's around 3 or 4. A lot of it is dependent on the individual components, the soldering, and so on. I actually changed. I had some real inexpensive caps that I had of unknown origin for the tank circuits, and I changed those out for some better caps because I had an awful lot of loss in the filter. So good components makes a difference. Let's watch what happens if I change one of the caps on the coils in the tuning circuits. So watch what happens as you'll see things start shifting left and right. So you can see I'm shifting the frequency as I adjust the caps. And a little bit of this is a little bit of a dance. You kind of adjust a little here, adjust a little there, until you kind of get the optimum setting, minimize loss, best looking filter shape, have it centered right where you want it. And if you want to see what it looks like kind of at a different scale, so that's with a 10 megahertz scan. Let's look at it with a 20 megahertz scan here. Span of 20. And gives you a nice look at what the nice steep skirts of the filter look like. So this will work really, really well for a 40 meter bandpass filter. I'm going to stop here, and then I'll show you kind of another quick way to look at the performance on the oscilloscope. So I've set up the signal generator so that it's generating a 5 megahertz signal at 1 volt peak to peak. I have one end going into one end of the filter. I have the other end of the filter terminated in a 50 ohm terminator, and I have the oscilloscope looking across that output port. And as you can see, at 5 megahertz, I basically have no signal coming through. So I'm going to start increasing the frequency. And as we get closer to the pass band, we'll see the... Now what we're looking for is when that peaks. So I'm at 6.2, 6.3, 6.5, 6.6, 6.8, 6.9, 7.1. That's 7.1 right there. And then as I go up, 7.2, 7.3, 7.4, 7.5, as we start to exit the pass band, we'll see that it starts to shrink, and by the time I get up into 8 megahertz, we're getting back down in the noise again. So that is the way to look at the filter performance using a signal generator and your oscilloscope. And you can get a sense of about where you are, about whether or not you're getting peak values, and then you can adjust you can set your frequency to the middle of the band, and then you can adjust the trimmers just the way I did before until you maximize the signal. So that's it for the bandpass filter. We will put it in place on the board, and next week we'll work on the audio amplifier, and we will have a complete direct conversion receiver. So for now, this is Dean, KK4DAS, saying 7-3.